Imagine you're scrolling through your favorite social media app, and suddenly you come across a post that seems tailor-made for your interests. It's as if the app knows exactly what you want to see before you even realize it yourself. This isn't magic. It's the result of sophisticated recommendation algorithms working behind the scenes. But what if I told you that the technology powering these recommendations is about to take a massive leap forward? Enter Generative Recommenders, GRs, a groundbreaking new approach to recommendation systems that is poised to revolutionize how we discover content, products, and services online. Developed by researchers at a major tech company, GRs represent a fundamental shift in how AI systems understand and predict user preferences. To understand the significance of this breakthrough, let's look at a concrete example. Netflix, one of the pioneers of personalized recommendations, uses a complex system to suggest movies and shows to its 230+ million subscribers. Their current approach relies on analyzing viewing history, ratings, and other user data to make predictions. But GRs could take this to a whole new level, potentially understanding not just what you watch, but why you watch it, and using that deeper insight to surface content you'll love but may never have discovered otherwise. Or consider Amazon, the e-commerce giant that has built much of its success on its product recommendation engine. GRs could dramatically improve Amazon's ability to understand the context of your shopping behavior and make much more nuanced and accurate product suggestions. This could lead to increased sales for Amazon and a more satisfying shopping experience for customers. Deep Learning Recommendation Models, DLRMs, have been the gold standard for large-scale recommendation systems for about a decade. Companies like YouTube, Facebook, and Amazon have relied on DLRMs to power their content and product recommendations, serving billions of users daily. DLRMs work by processing a vast array of different types of data, known as features. These features can include 1. Categorical features, things like user IDs, content creator IDs, product categories, etc. 2. Numerical features, metrics like click-through rates, watch time, purchase frequency, etc. The key strength of DLRMs is their ability to handle this heterogeneous mix of data and extract meaningful patterns from it. They use various neural network architectures to combine and transform these features, ultimately producing recommendations tailored to each user. However, DLRMs face several significant challenges. 1. Feature engineering. A tremendous amount of human effort goes into designing and selecting the right features for DLRMs. This is a time-consuming and often imperfect process. 2. Scalability. As the number of users and items grows, the computational demands of DLRMs increase dramatically. This has led to a plateau in performance improvements, even as more computing power is thrown at the problem. 3. Dynamic environments. Online platforms are constantly changing, with new users, new content, and new products being added all the time. DLRMs can struggle to adapt quickly to these dynamic conditions. Generative recommenders take a radically different approach. Instead of relying on carefully engineered features, GRs treat the entire history of a user's interactions as a single, unified sequence of events. This is similar to how large language models like GPT-3 process text as a sequence of tokens. To understand this, let's use an analogy. Imagine you're trying to predict what a person will do next based on their past behavior. The DLRM approach would be like having a detailed spreadsheet of their activities, broken down into different categories: work, leisure, social, etc., with various metrics for each. The GR approach, on the other hand, would be more like reading their diary, a chronological account of everything they've done without any predefined structure. This sequential approach allows GRs to capture complex patterns and dependencies that might be missed by traditional DLRMs. It's particularly well suited to understanding the context and evolution of user preferences over time. Key concepts of generative recommenders. 1. Unified feature space. GRs consolidate all types of features into a single time series. This eliminates the need for extensive feature engineering and allows the model to discover relevant patterns on its own. 2. Sequential transduction. The core tasks of recommendation systems, ranking and retrieval, are reformulated as sequential prediction tasks. This is similar to how a language model predicts the next word in a sentence. 3. Generative training. Unlike DLRMs, which are typically trained on individual user-item interactions, GRs are trained to generate entire sequences of user actions. This allows them to capture long-range dependencies and subtle patterns in user behavior. 4. Target-aware formulation. GRs can incorporate information about the target item, the item being considered for recommendation, directly into the sequential processing. This allows for more nuanced and context-aware recommendations. The key insight behind GRs is that a user's actions, the content they engage with, the products they buy, the searches they perform, contain incredibly rich information about their preferences and intent. By focusing on these actions and treating them as a coherent sequence, GRs can build a much more comprehensive and nuanced understanding of each user. This is where the title of the research paper, "Actions Speak Louder Than Words," comes into play. Traditional recommendation systems often rely heavily on explicit feedback, ratings, reviews, or simple implicit feedback, clicks. GRs, on the other hand, can interpret the full spectrum of user actions, understanding not just what a user did, but the context in which they did it and how it relates to their other actions. To make this concrete, let's consider an example from e-commerce. A traditional DLRM might see that a user clicked on a pair of running shoes and recommend similar products. A GR, however, could potentially understand that this click came after the user had been browsing training plans for a marathon and had recently purchased new running clothes. Armed with this contextual understanding, the GR might recommend not just shoes, but also energy gels, a running watch, or even books on marathon training, items that fit into the larger picture of the user's current interests and goals. At the heart of Generative Recommenders is a novel neural network architecture called Hierarchical Sequential Transduction Units, HSTU. HSTU is designed to efficiently process long sequences of user actions while capturing complex patterns and dependencies. Key components of HSTU. 1. Pointwise aggregated attention. Unlike traditional transformer models that use softmax attention, HSTU employs a pointwise aggregated attention mechanism. This allows the model to better capture the intensity of user preferences and handle non-stationary vocabularies. 2. Sparse computation. HSTU leverages the natural sparsity in user interaction data to dramatically improve computational efficiency. 3. Stochastic length. To further improve efficiency, HSTU introduces a technique called stochastic length. This allows the model to work with variable length subsequences of user history during training. 4. Efficient memory usage. HSTU employs several techniques to minimize memory usage, allowing for deeper models and larger batch sizes. 5. M-Falcon algorithm. For inference, HSTU uses a novel algorithm called micro-batched fast attention leveraging cacheable operations, M-Falcon. To understand how HSTU processes user data, let's walk through a simplified version of its operation. 1. Input sequence. The model takes as input a sequence of user actions, represented as tokens. Each token might represent an item the user interacted with, along with information about the type of interaction, view, purchase, etc. 2. Embedding. These tokens are first converted into dense vector representations, embeddings. 3. Self-attention. The core of HSTU is a series of self-attention layers. In each layer, the input is transformed into queries, keys, and values. The pointwise aggregated attention mechanism computes attention scores between each position in the sequence and all previous positions. This attention is used to create a weighted sum of values, capturing relevant information from across the sequence. 4. Feed-forward and normalization. The output of the attention mechanism goes through additional processing, including feed-forward neural networks and layer normalization. 5. Output. The final layer produces predictions for the next item in the sequence or scores for candidate items. Several innovations in HSTU contribute to its superior performance. 1. Pointwise attention. By using pointwise aggregation instead of softmax, HSTU can better capture the intensity of user preferences. 2. Efficient sparse computation. HSTU's attention mechanism is designed to efficiently handle sparse input sequences. 3. Stochastic length. This technique allows HSTU to effectively train on much longer sequences than would otherwise be possible. 4. M-Falcon. This algorithm allows HSTU to score large numbers of candidate items during inference. To appreciate the significance of HSTU, it's helpful to compare it to traditional DLRM approaches. 1. Feature handling. DLRMs typically require extensive feature engineering and rely on complex architectures to combine different types of features. HSTU processes all information as a single sequence, eliminating the need for manual feature engineering. 2. Scalability. DLRMs often struggle to scale beyond certain sizes due to computational complexity. HSTU's efficient attention mechanism and sparse computation techniques allow it to scale much more effectively. 3. Temporal understanding. While some DLRMs incorporate sequential models for certain features, HSTU's fully sequential approach allows it to capture long-range temporal dependencies much more effectively. 4. Adaptability. DLRMs can struggle to adapt quickly to changes in the underlying data distribution. HSTU's generative approach makes it inherently more adaptable to dynamic environments. On public datasets commonly used in recommendation system research, MovieLens and Amazon reviews, HSTU-based models significantly outperformed existing approaches. On the MovieLens 20M dataset, HSTU improved hit rate at 10 by 11.9% and NDCG at 10 by 15.9% compared to the previous state-of-the-art. On the Amazon Books dataset, the improvements were even more dramatic, with a 38.4% increase in hit rate at 10 and a 40.6% increase in NDCG at 10. The true test of any recommendation system is its performance in real-world large-scale applications. Here, the results are even more striking. 1. Offline evaluation. In retrieval tasks, GRs improved hit rate at 100 by 27.2% compared to state-of-the-art DLRM baselines. In ranking tasks, GRs reduced normalized entropy, a measure of prediction accuracy, by 2.7% for the main engagement task and 2.5% for the main consumption task. These may seem like small numbers, but in the world of large-scale recommendation systems, they represent significant improvements. 2. Online A/B testing. When deployed in a live production environment serving billions of users, GRs improved key engagement metrics by 12.4%. This is a massive improvement that could translate to billions of dollars in additional revenue for large platforms. 3. Efficiency. Despite being 285 times more computationally complex than the DLRM baseline, GRs achieved 1.5x to 2.99x higher throughput when scoring large numbers of candidates. This counterintuitive result is due to the efficient HSTU architecture and the M-Falcon algorithm, which allowed GRs to amortize computational costs effectively. Perhaps the most exciting finding is how GRs scale with increasing computational resources. The researchers observed that 1. GR performance scales as a power law with respect to the amount of compute used for training. This is similar to the scaling behavior observed in large language models like GPT-3. 2. This scaling behavior holds across 3 orders of magnitude, and 4, up to models with 1.5 trillion parameters. 3. In contrast, traditional DLRMs tend to plateau in performance as model size and compute increase beyond certain points. These results paint a picture of a fundamental shift in the capabilities of recommendation systems. Several key factors contribute to the success of generative recommenders. 1. Unified representation. By treating all user actions as part of a single sequence, GRs can capture subtle patterns and dependencies that might be missed by traditional feature-based approaches. 2. Temporal understanding. The sequential nature of GRs allows them to better understand how user preferences evolve over time and how past actions influence future behavior. 3. Efficient architecture. The HSTU architecture's ability to process long sequences efficiently allows GRs to consider much more historical context than traditional methods. 4. Generative approach. By framing recommendation as a generative task, predicting sequences of user actions, rather than a discriminative one, classifying user item pairs, GRs can capture more nuanced patterns in user behavior. 5. Scalability. The ability of GRs to continue improving with increased compute and data is a game changer. It suggests that we may see continued rapid improvements in recommendation quality as more resources are devoted to training these models. The most immediate and obvious implication is the potential for dramatically improved personalized experiences across a wide range of digital platforms. E-commerce. More accurate product recommendations could lead to increased sales and customer satisfaction. Amazon, for example, could use GRs to provide much more contextually relevant product suggestions. Content platforms. Streaming services like Netflix or Spotify could use GRs to surface content that better matches users' evolving tastes and moods. Social media. Platforms like Facebook or TikTok could use GRs to create more engaging and diverse content feeds, potentially addressing issues of filter bubbles and echo chambers. The ability of GRs to understand and generate sequences of actions opens up new possibilities for recommendation. Predictive assistance. GRs could power digital assistants that not only respond to requests, but proactively suggest actions based on a deep understanding of user behavior patterns. Personalized education. Learning platforms could use GRs to create individualized curriculum paths that adapt to each student's learning style and progress. Health and wellness. GRs could be used to recommend personalized health interventions or lifestyle changes based on a holistic understanding of a person's behavior over time. Despite their increased complexity, GRs can be more computationally efficient than traditional DLRMs when deployed at scale. This could lead to reduced infrastructure costs. Companies could potentially serve more users with less hardware, reducing operational costs. Energy savings. More efficient recommendation systems could significantly reduce the energy consumption of large tech platforms, contributing to sustainability efforts. The power of GRs also raises important ethical questions that will need to be addressed. Privacy. The ability to understand and predict user behavior with such accuracy may exacerbate concerns about data privacy and surveillance. Manipulation. There's a risk that highly accurate recommendation systems could be used to manipulate user behavior in harmful ways. Transparency. The complex, sequential nature of GRs may make it more difficult to explain why certain recommendations were made, raising issues of algorithmic transparency and accountability. The success of GRs opens up several exciting avenues for future research. Foundation models for recommendations. Just as we've seen with language models, we may see the development of massive, general-purpose recommendation models that can be fine-tuned for specific applications. Multimodal recommendations. Future work might explore how to incorporate different types of data, text, images, video, into the sequential GR framework. Causal recommendations. There's potential to extend GRs to capture causal relationships between actions, leading to even more accurate and useful recommendations. Federated learning. Exploring how GRs can be trained in a privacy-preserving manner using federated learning techniques could address some of the privacy concerns. The potential economic impact of GRs is substantial. Increased revenue. More accurate recommendations could drive significant revenue increases for e-commerce, advertising, and content platforms. Market disruption. Companies that successfully implement GR technology could gain a significant competitive advantage, potentially disrupting existing market dynamics. New business models. The ability to understand and predict user behavior with such accuracy could enable entirely new business models and services. The development of generative recommenders draws on and contributes to several other fields of study. 1. Natural language processing. The sequential, generative approach of GRs shares many similarities with large language models. Advances in GRs could potentially feed back into NLP research, particularly in areas like long-range dependency modeling. 2. Time series analysis. The techniques developed for efficiently processing long sequences in GRs could have applications in other domains that deal with time series data, such as financial forecasting or climate modeling. 3. Cognitive science. The success of GRs in modeling human behavior might provide insights into how people make decisions and form preferences over time, contributing to our understanding of human cognition. 4. Causal inference. While current GRs are primarily predictive, their ability to model sequences of actions could provide a foundation for more sophisticated causal modeling in recommendation systems. 5. Privacy-preserving machine learning. The challenges of deploying GRs while protecting user privacy could drive advances in privacy-preserving ML techniques like federated learning or differential privacy. Generative recommenders represent a quantum leap in our ability to understand and predict human behavior in digital environments. By treating user actions as coherent sequences rather than isolated events, GRs can capture the rich contextual nature of human preferences and decision-making in a way that was previously impossible at scale. The implications of this technology are profound. We stand at the threshold of a new era of personalized digital experiences, where AI systems can understand not just what we like, but why we like it, and how our preferences evolve over time. This could lead to more engaging content, more relevant products, and digital services that feel truly tailored to each individual user. However, with great power comes great responsibility. As we move forward with this technology, it will be crucial to address the ethical implications and ensure that these powerful recommendation systems are used in ways that benefit users and society as a whole. The future of recommendation systems is generative, and it promises to be an exciting journey of discovery and innovation. As this technology continues to evolve, it will be fascinating to see how it shapes our digital world and our understanding of human preferences and behavior.